Today we are going to review the Unit 6, which is Thermochemistry. Thermochem. Basically, this is the study of how heat flows from one place to another, specifically in reactions. Uh, so, a few terms that we need to define here. The system is what we are specifically trying to measure. The surroundings are everything else. The surroundings are everything else, basically. Together, these two make up the universe. However, often in chemistry, the system is actually just discrete ions, which cannot be measured. You can't stick a thermometer inside an atom, it doesn't work. So, we measure the temperature change of the surroundings. Now, we can do this because the surroundings, the immediate surroundings around the system, is going to be what takes all of the heat. You're not going to find your temperature change out somewhere else in space. So, uh, we do so. We use the surroundings to measure the system. So next, let's go ahead and let's go ahead and define endothermic and exothermic. Endothermic reactions, I'll say over here, and exothermic reactions are over here, we'll say, are two different types of reactions based on how much heat they gave off. Endo means in, and therm means heat, which means that this takes in heat. It literally sucks heat out of the surroundings and gets it for itself, which is why often endothermic reactions feel cold or cool. And for our unit of this unit, delta H, or delta H not often, is going to be greater than 0. Because if we draw our little energy diagram here of energy versus reaction coordinate, we can see that endothermic starts low, goes high for its activation energy, and ends off high. So this is the total activation energy. And this, for the purposes of AP Chem, will be delta H. So our delta H is taking a higher value and subtracting a lower value from it, which is always going to be greater than 0. Now, exothermic, on the other hand, exo means out, and therm, as always, means heat. This means it gives off heat. And they often feel hot or at least somewhat warm. And if we draw our energy diagram for this, they start off high, go to activation energy, and end off low. So, this is our EA, and this is going to be our delta H. So, when we're trying to find the sign of delta H, it is going to be subtracting a lower value, subtracting a higher value from a lower value, which is always going to be less than 0. So for exothermic reactions, delta H naught is always going to be less than 0. So, uh, let's move on. If my select tool will work. So now let's talk about something core to this unit, calorimetry. Calorimetry is indirectly measuring the heat of reactions. Like I said, for this unit, we need to measure the surroundings because we cannot measure the system directly. So, what we can do, and this is actually the only type of calorimetry that AP does, I believe, is what is called coffee cup calorimetry. If you go to a coffee shop, they'll give you these styrofoam cups, which you can use to make a calorimeter, which looks something like this. Your solution and your thermometer. It's not very uniform. So, this is called coffee cup calorimetry because quite literally it is made up of 2 coffee cups. Remember that we are trying to measure this energy of the system, not the surroundings. So, we use Q surroundings, which has the same magnitude as Q system. However, there's one thing to note here. The heat of Q surroundings. If it takes in heat, that means that the system is releasing heat. If it gives off heat, that means that the system is taking in heat. So we always say that Q surroundings is equal to negative Q system. Or, if you're trying to frame it in something that we're trying to measure, Q system equals negative Q surroundings. I'll abbreviate these SURR. So, the actual quantitative way to measure this is to say Q equals mc delta T, where Q is heat, m is mass, C is specific heat, usually given in the question, and delta T is change in temperature, or, well, T. So, let's do a little practice problem, shall we? So, we'll say that a hot metal bar of metal M is dunked into the water. Now, the water is initially at 22.0 degrees Celsius. After the metal bar is dunked in, it raises the temperature to 26.5 degrees Celsius. So, what is the total amount of heat that was given off by the metal bar? Okay, so we use our trusty equation Q equals mc delta T. If you're wondering how we get M, we can weigh the empty coffee cup calorimeter, zero the scale, fill it up with water, and that's how we get the mass. Which in this case, after we do all of that, will be M equals 100.0 grams. C will be given. However, I've taken so many chemistry problems that I have it memorized as 4.184 joules per gram Kelvin. And delta T is going to be 26.5 minus 22.0. A quick note here. You'll notice that I'm writing 22.0 instead of just 22, even though the two are mathematically equivalent. AP loves significant figures. So, as a brief rule of thumb, however many significant figures you want to give the least amount. Uh, don't give one arbitrarily. However, you're going to want to give the least amount of significant digits offered in the question. In this case, 3, 22, 3, as given in our temperature. So let's calculate it. I have my own calculator here. So let's see here. 100.0 times 4.184 times 26.5 minus 22.0. And I get Q equals 1882.8 joules. Now remember, this is Q of surroundings. If we want to find Q metal, we just simply reverse the sign. And that is equal to negative 1882.8 joules. Now we take into account significant figures. So Q metal, sorry I misspelled this, metal is equal to negative 1880 joules. Do it in kilojoules, which AP loves, and you get 1.88 kilojoules. So now that we've covered calorimetry, let's move on. So a little something you might have noticed about water is that it has different states. One being ice, one being liquid water, and one being gas. So what we can do is we can actually plot the amount of energy that we give to the water and measure the temperature. So we'll say that this right here is 100 degrees Celsius. This is negative 10. We'll say here is 0. So let's apply some heat to some ice at negative 10 degrees Celsius. So it constantly heats up until it reaches 0, at which point it undergoes no temperature change. This is actually by definition. At the point which there are no liquid water molecules left, we start to increase the heat again. Notice how the slope is less shallow, or more shallow. This means that the liquid water, has a higher specific heat than solid ice. Liquid water specific heat is about 4.184, and solid ice specific heat is about 2.19. So now we've reached the point where the water boils, and once the water boils all the way, the water can increase in temperature again. So let's go ahead and move on to thermochemical equations. Actually, no, we aren't moving on. We're going to go ahead and address some phase changes. So phase changes, as you might have noticed, happen all the time. If we use the example of water, we have ice, water, and gas-ish water. So we can say solid, liquid, gas. Solid turns into liquid, liquid turns into gas can turn into solid, and liquid can turn into solid, gas can turn into liquid, solid can turn into gas. So, I'm going to draw a supersized model here. So solid can turn into liquid, liquid can turn into gas, and gas can turn back into solid. So, and these processes can happen in the other direction as well. So, solid to liquid is called fusion. Liquid to solid is just called freezing. Liquid to gas is called vaporization. Gas to liquid is called condensation. Solid to gas is called sublimation. And this actually happens with dry ice, if you've ever heard of it. That is solid carbon dioxide. Liquid carbon dioxide cannot exist at room temperature and pressure. Therefore, solid carbon dioxide goes straight to gas carbon dioxide. So you have sublimation, and then uh, gas to solid would be deposition. So now, what if you want to say know the delta H values? So delta H naught of fusion, vaporization or vap, and sublimation or sub are always going to be greater than zero. This is why this is actually why melting things feel cold or sublimating things feel cold. The cold thing is leaching heat out of your hand in order to aid in its melting or sublimation. Dry ice is actually so cold that you will burn yourself if you do not have proper protection. However, on the other hand, delta H naught of freezing, condensation, and deposition are all less than zero, which means that they give off heat. So, let's move on to stoichiometry / thermochemical equations. So, thermochemical equations basically are just chemical equations with a delta H naught value assigned to them. If we use the example of hydrogen bromide, these are both gases. This is a gas, this is a liquid, and this is a gas. We can see that the delta H naught value is approximately equal to negative 72.8 kilojoules per mole. Now, this represents forming 2 moles of HBr. However, if we are to cut it in half, we get 1/2 HBr, H2 plus 1/2 Br turns into 1/2 Br, which turns into delta H naught equals negative 72.8 over 2, which is negative 36.4. So now, let's go on to something called Hess's law. Hess's law basically says that if you have any series of reactions that add to a total number of total reaction, right? I'm using dots here because I want to go to sleep. It is 1 a.m. as of the time that I'm recording this. Then delta H naught 1, delta H naught 2, and so on to delta H naught n turns into delta H naught of total or reaction is equal to delta H naught 1 plus delta H naught 2, and so on and so forth until you get plus delta H naught n. So let's do an example. I have the reactions H2 plus Br2 turns into 2HBr. And I also have the equations H2 plus 1/2 oxygen turns into H2O. I have the delta H naught values as negative 72.8 kilojoules per mole. And this delta H naught value is equal to negative 285.8 kilojoules per mole. Say we want to find the reaction equation, not the reaction equation, the delta H naught value of the reaction H2O plus Br2 turns into half an oxygen plus HBr, two of them. Then what would the delta H naught be? Well, it's simple. Really, you flip the second equation, putting H2O on the reactant side and H2 on the product side. You can add the two reactions together, H2 will cancel, and Br2 and water are left on the reactant side, and half an oxygen and 2 HBr are left on the product side. Now, I'm going to calculate this. So, since we did not do any fancy division or multiplication, we can just straight up use the delta H values. Since I flipped the second equation, I flipped the sign. 285.8 minus 72.8, and we get 213 kilojoules per mole. Now, let us move on. And to enthalpies of formation. Enthalpies of formation, sorry, wrong, I'm getting ahead of myself, we can move on to bond enthalpies. Bond enthalpies are basically saying that for a reaction A plus B turns into C, then the delta H naught value is equal to the bonds broken minus the bonds formed. This is a very rough estimate because it does not take into account states. If we use our example of H2 plus Br2 turns into 2HBr, H2 we can see is 436, HBr is 364, and Br2, I don't have it on the table, however, I have another source on the other screen that says that it's 193 kilojoules per mole. 193. So, we say delta H naught is equal to bonds broken, 436 plus 193 minus bonds formed, minus 2 times 364. Now this is equal to, I'm going to do this on my own calculator, plus 193 plus 436 to get negative 99 kilojoules per mole. Okay? So, now we can actually move on to bond enthalpies. Not bond enthalpies, enthalpies of formation. Sorry, I'm tired. Enthalpies of formation is the amount of heat that is required to make 1 mole of that substance. Now you'll notice, silver solid 0, bromine 0, calcium solid 0, chlorine gas 0, fluorine gas 0, hydrogen gas 0. And that is because delta H naught of formation for a pure element is always going to be equal to 0. So, we can actually take our HBr value, negative 36.4, and subtract it by, well, nothing. Since the reaction equation is 1 half H2 plus 1 half Br2 turns into HBr. And this then is the enthalpy of formation. Now remember, if they give you enthalpies of formation, you use the enthalpy of formation. If they give you bond enthalpies, you do not try and figure out the enthalpy of formation just because bond enthalpies are an estimate. You figure out the bond enthalpy. Now, I'm assuming that you're watching this before a test, so good luck on your test, and I will see you all later. Bye-bye.